In this video, we are going to do another Lagrange multipliers example, but in this question, we're going to minimize a sum of squares. So the example says, find 4 real numbers, summing to 20, so that their sum of squares is as small as possible. Okay, so I want to begin by identifying my objective equation, so the quantity that I want to maximize or minimize. In this case, because the problem tells me as small as possible, I know I want to minimize something. Small as possible, that tells me I want to minimize something. So what is it that I want to minimize? I want to minimize the sum of the squares of these numbers. So I don't have a name for that thing, so maybe let me call it S for sum. And I don't have variables assigned to these 4 numbers, so maybe I'll just call them A, B, C, and D. So A, B, C, and D. So S is the sum of their squares, so A squared plus B squared plus C squared plus D squared. And that's my objective. Okay, I can also write this in function notation as a function of, in this case, 4 variables, A, B, C, and D, and say that function is A squared plus B squared plus C squared, let's write that better, C squared plus D squared. Okay, so my goal is to find the minimum value of this, or at least to find the 4 real numbers that make me have a minimum value, make this function have a minimum value. Okay, but we also have a constraint in this problem. So the other piece of information the problem tells me is that these 4 numbers sum to 20. So that means that A plus B plus C plus D, their sum is 20. So we can move everything over to one side and get our function g. So g of A, comma B, comma C, comma D, if I move everything over to one side, I would get A plus B plus C plus D minus 20. Remember, that was our convention for attaining the function g. We take our constraint, and technically we just need to move everything over to one side so that the other side is equal to a constant. Usually the convention is move everything over to one side so that the other side is equal to 0. Well, that's what we've done. And when we do that, the non-zero side is our function g. Okay, so now we are ready for some Lagrange. We set the gradient of f equal to, actually no, I need to take gradients first. Okay, getting ahead of myself a little bit. So the gradient of f, first let's take the partial with respect to a, that's 2a, and the partial with respect to b, well, that's 2b. And similarly, the next one would be 2c, and then the next one would be 2d. So we actually have a function of, a vector function of 4, with 4 entries here. That's okay, we can handle this. And then the gradient of g next. So the partial with respect to a, b, c, and d, they're all going to be the same here. They're all going to be 1. They're all going to be 1. So now we are ready to set the gradient of f equal to lambda times the gradient of g. So when we do that, we're going to get a system of equations. So the first equation that we'll get from setting their a components equal would be, we'll have 2a from the gradient of f equals lambda times. So this is from setting this component, and then lambda times this component equal. So we'll get lambda times 1. Okay, and then we do the same thing for the next entries. So we'd get 2b is going to be equal to lambda times that corresponding component, which is 1 again. Okay, and then we'll get 2c is equal to lambda times 1, and 2d equals lambda times 1. Okay, so that's just from setting the components of gradient of f equal to the components of lambda times the gradient of g. So remember that our system of equations isn't done here. We get to write one more equation that comes from the constraint. So the constraint was a plus b plus c plus d equals 20. Okay, so that's how we get a system of equations. In this case, we have 5 equations with 5 variables, a, b, c, d, and lambda. All right, so this example is actually simpler than the one that we did before. It's easier to solve. I know from equations 1 through 4 that lambda equals 2a, lambda equals 2b, so I know lambda equals 2a, and lambda equals 2b, so those are equal, and lambda equals 2c, and lambda equals 2d, so 2a and 2b and 2c and 2d are all equal. And collectively now, if I divide these last four terms all by 2, we get that a equals b equals c equals d. So all of those variables need to be the same. So if we use that to substitute into this last equation, we'll end up getting a plus a plus a plus a equals 20. Okay, so that means that a is equal to 5. And because the other variables are all equal to a, this means that a equals 5 and b equals 5, and same thing with c, and same thing with d. All of them equal 5. So we just have this one solution to our Lagrange system of equations. Okay, so now let's analyze this. So I need to ask myself, is this solution that I got a min or is it a max? Okay, so what I want to note first is, if we experiment a little bit with our function, it's really easy to satisfy the constraint. In fact, if we let a be 20, and then I'll think about the other variables in a sec. So b is something, and c is something, and d is something. But at this point, we would get, I want to pick values for a, b, c, and d that satisfy a plus b plus c plus d equals 20. So what would sort of satisfy this? Well, I made a be 20 for a reason. What if I just made the last variable be 0? It's going to be satisfied, this constraint is satisfied, as long as b and c are opposites. So what if I just made b be any real number? Any real. And I just made c the opposite of it. So c is going to be equal to negative b. That would satisfy a plus b plus c plus d being equal to 20. While if I look at the objective function, a squared plus b squared plus c squared plus d squared, that would be equal to 20 squared plus b squared plus negative b squared plus 0 squared. And simplifying this, 20 squared is 400. And then negative b quantity squared is just b squared. So I'll get b squared plus b squared, which is plus 2b squared. And in this expression, b can be any real number. And because of that, this could be as big as we want it to be. It can be arbitrarily big. So this has no max. And if that has no max in this specific case, well, that means our objective function in general is not going to have a max. So as a result, this solution that we found, therefore the solution a equals b equals c equals d, where they're all equal to 5, this definitely isn't going to be a max. We just said our objective doesn't have a max. This makes the sum of squares minimal. Okay, so the answer, this problem asked, what are the 4 numbers? So the 4 numbers, well, they're all equal to 5. If the question had instead asked, well, what is their minimum sum of squares? Well, I would take those 4 5s and I would plug them in to a squared plus b squared plus c squared plus d squared, and that would tell me what the smallest possible value of that function is, subject to this constraint. Okay, so let's go back up to our work here. Okay. All right, so there are 2 important questions that I want to sort of reflect on now. So the first is, we've mentioned that with Lagrange, it gives us local extrema. But when we do these optimization questions, we're trying to find absolute maxes and absolute mins, these constrained optimization questions. So how do we know that our local min, when all the 4 variables equal 0, all the 4 numbers equal 0, is actually the absolute min, like we're after? We're trying to find the absolute min. So the answer to this, and this ties into a question I was sort of had posed in the previous video. is to think about, well, what if it wasn't the what if this wasn't the absolute min? If it wasn't the absolute min, Lagrange would have produced another solution and the reason for that is, if I were to just draw the graph of a function of one variable, so just on my x and y axes, if I think about having a local min, so local min would correspond to like a point where, sort of like that, it's a local min value. But for that local min not to be an absolute min, I would have had to have a situation where the function, changed, and went lower, went even lower. And I don't know what it does sort of at this point. Does it like keep going down infinitely, or it just needs to go below this local min point? But for it to go below that local min point, there would have to be another place like this, where it sort of changed direction to go lower, and it would have had to given me a local max point. It might have also given me some point over here where it had another local min. But in any case, Lagrange would have had to produce this other solution. At the least, it would have had to produce that local max where it sort of changes direction and starts to go down lower. But in this question, it didn't here. There was only one solution. And that's how I sort of know, oh, there wasn't this local max where it could have changed directions and went even lower than where my local min was. So we're sort of arguing, this is sort of called arguing by contradiction a little bit here. I wouldn't worry about the details or even the name of that, what I just said, arguing. Technically, it's like a proof by contradiction. I wouldn't worry about that detail. I care most that you just understand this logic here. How do we know that it's an absolute min? Okay, so there's one more question that I wanted to ask about this, which is, why didn't Lagrange in this problem also give us a max? Like, we went through the algebra a little bit and showed that our function doesn't have a max because it can get as big as possible. But how come Lagrange didn't give us any local maxes? Like, it gave us a local min, how come it didn't give us any local maxes? And the answer to that is, there was a theorem in section 14.7, a previous section, that says that a function attains its absolute max and min on a closed bounded region. On a closed bounded region. But our constraint, which is a plus b plus c plus d equals 20, is unbounded. It is not bounded. So by unbounded, I mean there are places where it could sort of go off to infinity. And I want you to think about, why is that? Why is this equation, a plus b plus c plus d equals 20, unbounded? But for our purposes, because it is unbounded, that means this theorem from section 14.7 doesn't apply. That's why it's okay that our function here didn't have, that's why it's okay that our function didn't have an absolute max, but it did have an absolute min. That's why it's okay. And because this condition, that it be closed and bounded, was not satisfied. And at that point, this theorem no longer applies. So if our constraint does correspond to a closed and bounded region, as it will in our next video, then this theorem says there should be an absolute max and an absolute min. So we'll see that in the next video. But in this problem, it does not apply because our region is unbounded.